He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
It would be fair to say we know more about the surface of Mars than we do about the surface of our own planet, because you can't see through the ocean. You've got to go down there and look. You've got to go down there with something to see.
Kia ora. Nau mai haere mai ki te ao hurihanga. Hello and welcome to Our Changing World. Ko klek and kana ho. Now, it's not a new sentiment to want to explore the ocean floor.
This is a motion picture studio 165 feet under the sea. These divers, wearing the compressed air aqualung, are true spacemen, swimming free as fish.
Jacques Cousteau brought the underwater realm alive with his aqualung scuba invention and 1950s documentary, The Silent World. Since then, we've discovered it's very much not silent down there, but there's still so much to learn because, well, humans are just not really built to be underwater. In this episode, Liz Garton heads to the Auckland Bioengineering Institute to see some of the latest tech that might help in future ocean explorations. Tech like robot fish.
We have flying robots, like drones. Companion robots.
Meet Ilek, a little desktop companion bot with endless fun.
Pardon me, may I get to that spot, please?
Meet Moxie, the robot.
Even health bots.
A high-tech nurse's helper rolling through hospitals around the country.
But when I heard that the Auckland Bioengineering Institute, a place where some of the cleverest people in New Zealand and from around the world work, was developing fish robots, the thing that first came to my mind was a toy I once bought my kids for Christmas.
Robofish burst to life in water and swim just like a real fish.
Sadly, our robot fish didn't last very long. And look, it didn't do anything particularly interesting, except swim around in the bath. So I had to wonder what these very smart people were up to and why.
To your left.
Professor Ian Anderson, group leader of the Biomimetic Lab, met me at the ABI offices in central Auckland to give me a bit of a tour.
Yeah, so that's the submarine Taniwha.
So Taniwha, one of the team's first forays into fish-like machines, was built nearly 10 years ago. It's a human-powered submarine.
It's operated by fins at the top and bottom there. You've got the pilot who is breathing on scuba is paddling the submarine from the inside and making these fins move. It sort of kind of resembles a leather jacket in a way, with the fins flapping at top and bottom like that.
In 2015, Ian and his colleagues raced Taniwha at the International Submarine Races in Maryland in the US.
And we won. We won the top prize, and against 10 other teams from around the world.
Now, the sort of tech we're looking at today doesn't involve a human in a very, very small enclosed space underwater. I can tell you, I would not be getting in there. Today's tech is robot tech. They're taking the human out and putting the fish in.
At the moment, we're looking at propulsors, which are quiet. Fins are quiet, so they don't disturb marine life, and they also don't get clogged up with the weed. If you have a little propeller, it sucks the weed in, and it gets jammed. You're not going to get your fingers chopped off in a fin. So that's been one of our motivations, is to try and find a way to give underwater vehicles fish-like presence.
There are many benefits to having fish robots, and we'll come to them soon. But how the machine propels itself around isn't the only step in making it more fish-like.
One of our focuses is to look for ways of making robotics soft and more bionic or biomimetic, like the name of our lab. And so the idea is to go from robots which are steel and hard plastic to made of silicone and soft materials, which are more living-like, and also to give them living-like attributes, such as like quiet actuators that move and create force without gearboxes, and also to sense. We sense everything through our fingers and our skin, and one of the motivations is to try and find a way of giving us the ability to sense very light levels of touch on robotic-like skins. We have a lab here for making soft robotic stuff out of silicone and other soft materials, and we also have a little bit of a workshop to build our stuff with. And allow me to introduce you to the group.
The first person I'm introduced to is a PhD student originally from Germany. I'll let him pronounce his name.
I have a German version, which is Arne Bruns, but internationally, people just call me Arnie. It's just easier. I prefer it.
Like the ex-governor of California.
Yeah. I mean, very close resemblance. But yeah, just Arnie.
We'll come back to Arnie and the work he's doing to make sensors for robot fish soon. But I'm also introduced to Robin Millward-Cooney, another PhD student.
What I'm working on is artificial mussels. They look like this. They're 2 layers of, you can touch it?
Ooh. Yeah, it's a bit squishy. It looks just like a bit of plastic with liquid inside.
And the way these work is that these form a capacitor, and the fluid gets pushed to one side of the membrane, and then that, depending on the shape of the polymer sheets, you can make different motion by moving the fluid around the different channels.
Oh, gotcha.
Yeah.
So this is what you're talking about with making it more human-like, more
human-like
soft.
Yeah, so
Is
this is like you can just crunch it up in a ball,
and
it won't. Well, it shouldn't break.
If you made it right.
If you made it right, yeah. But obviously, conventional motors and actuators, they're all like rigid and have like a rigid structure around it. So I guess my project is moving away from that, especially with underwater stuff like propellers are quite noisy. So to try and replace propellers essentially.
Robin's working on a Ministry of Business, Innovation and Employment funded project to make a quiet submersible that can be used to patrol the reefs of New Zealand. As Ian says, to do reef surveys
without frightening away the fish.
The plan would be to have Robin's robot mussels and Arnie's robot sensors working together. But as Arnie says, they're not quite there yet.
It's, as we say, future music. So if at some point we can combine it, that his artificial muscles respond to my artificial sensors, and then they work with a control unit under it with a computer program to make the fish actually move like a fish, because it propels like a fish and senses like a fish, and then it's not quite a fish, but it's pretty close to a fish. It's pretty close to a fish. It's basically a fish.
Ian and I continue on around the office, which looks like your classic office setup with shoulder-height partitions breaking the space into cubicles, desks covered with computers and stationery. Although these desks also hold tools and electronic parts, so maybe not so common in most offices. But the most unusual bit had to be when I hit the desks of Dr. Derek Orbar-Antillon and PhD student Cheng Huan Liu. Because Derek's wearing a wetsuit.
You see, we go underwater regularly.
Yeah.
We have, look, this guy's got, is all wired for sound.
Yeah, wow.
So
not your average wetsuit then. There are sensors all over Derek's chest and a box with wires coming out of it like an octopus at his waist.
Yeah, the idea is to enhance diver safety during a mission. For that, we're developing this vest that will monitor the physiological parameters of a diver. And this basically will monitor all the diver kinematics to have an idea of what the diver is doing underwater.
There are 7 stretchable sensors on the wetsuit to monitor leg movements, and so far they've identified about 8 different styles of swimming.
So this is helpful for various reasons. One of them can be having proper form. So if you're dragging your legs down, this is going to cause the diver to become more fatigued and therefore consume more air. And the air is the most important resource we have underwater. And then if you're also, let's say, dragging your legs down, you can hit the coral reefs or sand, which will create silt, and this will reduce the visibility underwater.
The feedback from the wetsuit could go straight to the diver so they can correct the way they're swimming, or it could go to a buddy, say if the diver was in trouble.
But if you're having like a panic attack, it's going to tell your dive buddy to turn around and assist you. Because telling yourself that you're having a panic attack is not a very good idea.
In the future, Derek and Cheng Huan will be looking at using the stretchable sensors to identify arm movements too, so the suit can communicate exactly what the diver's doing, whether that's welding a deep-sea pipe or monitoring changes to coral reefs. But there's another way to detect what's happening with divers underwater, and that's through their heart rate and brainwaves. For this, Cheng Huan is developing specific hydrogels that will sit inside the wetsuit to monitor those functions.
We're trying to make some new underwater material. So this hydrogel is used underwater and we can detect the impedance on the body. All the other material cannot do the same thing, so that's what we focus on right now.
Yeah, one of the challenges is measuring ECG signals underwater and EEG signals underwater, or like any impedance across the body.
Quick sidebar, impedance is the opposition to flow of alternating current. I googled it. Essentially though, it's something that's factored in when you're measuring the body's electrical signals. The key point here is that when you're doing an ECG underwater, you want to be measuring the signal through the body, not through the water.
So that's why we're developing this specific hydrogels to be able to measure heart rate underwater and the impedance between different points of the body, and hopefully in the future also brainwave signals.
From there, the trick is delivering the data collected by all these sensors. And look, I can say the box with all the electrical wires coming out of it, it doesn't look particularly water friendly right now. But Derek assures me they've got a plan.
Ideally, this will go under the wetsuit, and then we'll have just this board that will connect through inductive communication, or let's say Bluetooth. So Bluetooth can communicate underwater up to like a meter distance. So we'll have that on the inside. And then on top of it, we'll have the wetsuit, which will have the big acoustic modem to transmit with the surface and divers. And we'll also have like the brain or the control system.
Derek says they've managed to squeeze all this into a 3x3 box that's about 6 centimetres long.
The biggest component is the acoustic ring, which enables us to communicate long distances.
Because, as Em points out, acoustics are by far the best way to communicate underwater.
Sound is the mode of communication in the sea. Whales communicate over incredibly long distances with sound.
They're pretty confident the underwater communication system they're developing will work, thanks to a glove they developed a couple of years ago, which recognises diving hand signals.
The glove recognises the gestures, like, for example, are you okay? Shall we end the dive? Let's go up. And converts it into a message that can be transmitted in 1 byte. And this then is transmitted acoustically. So I can communicate with my diver buddy even if he's behind me. And it also uses as a property of sound waves that they can bounce off surfaces. So if there's an object between us, I can still send the message and it will bounce off the surface or the floor, and it will be received by my dive buddy who has, let's say, another glove, and then receives the message either through haptic feedback, LED colors. So for example, if I were to send you, I have a problem, the signal will be red. So I'm probably a very intense vibration. Mm-hmm. If I'm just asking if, are you okay? It might flash green a couple of times and give you like tiny vibrations just to get your attention.
The team proved the power of this sort of communication by using the glove in a pool in West Auckland to direct a robot in a pool all the way across the world in Croatia. Here's Ian.
One of our guys did the gestures, transmitted a signal acoustically to the side of the pool. It then was picked up by an acoustic modem, went up to the computer that Derek was operating. Then that went over the internet to Croatia. Then the Croatians then sent the signal down to the side of their pool and then acoustically through to their robot. Wow. And we moved the robot essentially via the internet and water.
Although Derek and Cheng Huan's work is very cool, and testing did involve a robot, their wetsuit is not what I'm here to see. I'm here for the work of Arnie Bruns, which is funded by the Office of Naval Research out of the US.
Essentially, a lot of people are trying to develop fish-like robots. It goes back to like the 90s at MIT where they first designed the robotuna.
The robotuna, as they're calling it, doesn't rely on traditional means of propulsion like propellers or jets, but it actually swims by flipping its tail. And by swimming like a fish, it's able to move stealthily and accelerate up to 40 knots, or about 46 miles per hour.
One of the problems you always have that if you want to swim like a fish, you got to sense like a fish, and that's a big challenge.
Arnie takes me over to a glass tank which is full of water. It's not huge, it's about 150 centimetres long, half as wide, and about 20 centimetres deep. On its top, there's a motor and lots of controls, which all connect up to Arnie's computer.
This is our sensory testing setup, so we We had it actually made on the South Island. An engineer made this water tunnel for us, where we have a propeller that speeds up the water, sends it around, makes it all nice and smooth, and then we have a test section where we can test the different sensors' behavior. Essentially, we can make sensors here in the lab, and then instead of having to go to the ocean, go to a big testing facility, we've built this one to have like instantaneous measurements. So we can test something, correct something in the sensor, come back, do it again. Goes up to almost 2 meters a second.
Inside the tank, in the water, is a little fishtail-shaped triangle of what looks like plastic with some black fluid inside.
It essentially is just a bit of silicone. Like a lot of people know it from, like, say, medical products like heels, things for your shoes. It's essentially just silicone and carbon. That's kind of all it comes down to, and then precision, extreme precisions in manufacturing, to be able to get the layers so thin. So what I've produced or what I've developed are these very thin membranes. They're about 1/3 of a millimeter thin and 7 layers of material, creating like a capacitor. It's like 3 electrodes stacked kind of in that fashion. And as this membrane stretches from the water flow, the capacitance, the electrical properties of this thing change, and we can pick that up. This basically, it's printed electronics. So it's not the traditional copper wire, but it's carbon. So it's conductive carbon, and we make these inks and then blade cast them to 50 microns thinness. So it's about a hair. And make these structures to create these sensors, which then we can test in the water. The membrane itself is the sensor. So this is basically this membrane is the whole sensor. We just have some wires on it to pick up that signal.
We're also mimicking what fish do, because they have, fish, you've got those rays that you see in the fins. Then you've got this membrane material between them, and all that's innervated. So what Arnie's developed here is a fish-like stress sensing membrane.
And I'm investigating how does the thickness of the membrane influence things, because fish can actively spread these rays to change the tension in the membrane. So I'm investigating how does that influence it, how does the amount of different fin rays, so you have the external ones, but then I also include like thinner, very thin PET strips in there to mimic the rays in the fin. I'm basically investigating how can we best design these fins to give us the sensation that the fish have in their fins. And we can test them in these water tunnels. And I'll just turn this one on. And we have a control unit up here that turns the fin into the flow. So slowly but steadily, we're changing the angle of attack between the water and the fin. And you'll see the membrane bulges out as the flow gets stronger and then tensions. And we can pick up that signal and then determine at what speed is the water flowing at the moment and what angle of attack do we have. Goal is that if a fish propels itself with its fins, we want to know how much force did it put on the water, how much are we moving forward, how effective was this, how much energy have we used. So it's very, as you can see, it bulges out quite a bit. And then it returns back.
So how is it telling you these things?
It's all about calibration in the end. So you collect some raw data, and then you have to take measurements of what that data aligns with. So we know the water speed, we know the area, we can do fluid simulations of how much force is being exerted onto the membrane, and then we can look at our data and say, okay, if we get this signal, that means this amount of force onto the fish. Then if we install the sensor in the fish, we get a signal that we know what it means in terms of force.
So Arnie's been running weeks of experiments to identify those profiles and quantify the effects.
The question of how do you process the data then, that gets more interesting. Like it's programs we write, and the goal is, of course, to get it in real time. We're not quite at real time yet. At the moment, we collect the data, process it, and then analyze it. The goal is to get picking up the data, analyzing it, and then getting a result from it basically in real time or very short time frames. And you might be wondering, like, so why are we doing this at all? Like, okay, you have a fish robot, and like, why are we trying to build all these sensors? So when you have a fish robot, in opposite to a drone that has propellers, very loud, scares everything away. Fish robot obviously silent, like all the other fish around it. But a fish robot has very limited space, so it's not very large. It's not like these other underwater robots that you see the size of a bus, or with cables. You have just a fish, and that's it. So you have very little space for batteries and for power supply. So if you want to have, you want to go deep, or you want to go far, or want to spend time underwater with the fish robot, you need high efficiency. And the fish robots that exist, and there's some commercial ones, they're more for show, and they're more for fun, or they look pretty, or for film. They have about an hour of battery time, and they just flop and do the same thing And with these sensors, you can get more feedback of what's happening, and you can adapt your swimming in a way that saves you a lot of energy.
Much of our work is focused on trying to measure what the water's doing around the fish. So Arnie's shown you a fish-like robotic fin that can sense how much force the water's imparting on it. But one of our overarching goals is to be sensitive enough to be able to detect what's happening upstream.
Yeah, the fish have these organs called the lateral line. We say it's one organ, but it's like saying the skin is one organ. So it's sensors that measure acceleration, they measure speed, they measure turbulence, and they have it all over their body. Some on the head, some on the body. They're very specifically tailored for different tasks, for detecting vibrations if they're fish that hunt, for flow speed, for the water flow separating from the fish, as in tunas, because they're very dependent on the water staying nice and laminar around it. So they're like minuscule. We're talking like little hair cells all over the body. And other research groups have mimicked them maybe 10, 15 years ago. But they're very fragile. They're extremely fragile. If you basically touch them, they break. So not that great for, marine environment on a boat. So we're trying to get the same functionality as the lateral line, but we're trying to do it extremely robust. So we're not copying it, but we're being basically inspired by it, trying to get that kind of same output.
A fish can feel, by feeling the water, they can tell they're in proximity to a surface. And this could be extremely useful for navigating in zones where there's very little light.
In like reefs, if you want to investigate reefs, caves, all that kind of stuff. At the moment, if you want to go into a cave, you have a cave diver, and it's incredibly dangerous.
So sensing the water around you is a very good thing to be able to do.
Arnie's work developing the sensor, getting all this data that can tell us what's happening underwater, is interesting. But what is he going to do once he's got all that information?
Like sensory data without an action is kind of useless in a way. What the fish does with it is it gets that sensory information, puts it through its brain, and adapts its swimming behavior to it, or adapts its motion behavior to it, or turns its head sideways because it knows there's a shrimp there that it wants to eat. And we want to do the same thing for a fish robot. So we want to build a fish demonstration robot, take our sensors, put them on there, and put this robot in different scenarios, and using machine learning in the end, like a brain, teach it new situations and have it react to outside input. To either swim more efficiently or adapt to different flow conditions or to react to outside water motions. So if we basically shove water at it, it will sense it and then be able to turn. That's kind of the idea behind it. There's a lot of research done on fish robots itself and the propulsion. Some people try to do it like a manta ray. Some people try to just flip with the back. There's all kinds of different approaches. And so far, nobody has built like the optimal robot yet.
At this point, Arnie showed me a demonstration robot fish made a couple of years ago.
It has a rubbery neoprene skins with sensors embedded into it, so you can tell at what angle the tail is currently pointed at. And we put some sensors in the front. You could push the eye, and then it simulates water flow, and then the tail moves. It's just to get people like interacting with your technology, because we obviously can't just put it in the water.
And is this the size you're looking at?
We're looking at something bigger.
Bigger?
So we're looking at this is a wahoo, so it's a New Zealand starfish, but like kind of what I'm more looking at and what I'm designing the sensors for is more tuna-sized, tuna-shaped, like 1.5 meters. Just because tuna are the most efficient swimmers, and they're big enough to put in all the electronics, the battery. If you have a tiny fish, you have a tiny battery.
So your tuna, in the end,
Yeah.
it will have the fins that you just show me, and
yeah.
maybe some eyes.
It might have this in the front to see how much it wiggles. So one good measurement of how efficiently a fish swims at high speeds is how much does the head turn left and right. Ideally it's 0, but the robots currently don't have 0. And you want to know how much is my head wiggling, and then adjust your swimming behavior or countermeasures to get the head pointed as much into the flow as you can. So that would be on there. And then a third one we're using these soft composites. It's also carbon and silicone, slightly different measurement way, but it's kind of like a fin on the back of the fish. There's these dorsal fins, and it picks up side to side motion. So if the robot fish is turning, or if it's turning a corner, or there's a turbulence coming, we're building these things that would also be on the top or on the side.
The ultimate aim, as Arnie said earlier, is mimicking nature.
Most biological systems don't just have one sensor for one task. Like, you can see the wind moving in the tree, you can feel the wind on your skin, all these kind of things. So if one fails or one doesn't work in the situation, you have redundancy. So the goal of my PhD is basically to build a cornucopia, big breadbasket of sensors and put as many different sensors on the fish. You get this very chaotic data from all the different sensors, and then it learns that. And when it recognizes the same kind of pattern again from all the different sensors, it knows essentially I'm in the same condition again, and then we can program it how to react to this condition. Saying they're swimming along Piha Beach, as an example. And at some point in Piha, there's the rip. So the fish swimming along, it's doing its thing, the sensors are all giving a similar input. And suddenly the sensors at the front of the fish start detecting a push from the side. And it notices that the other sensory input starts changing. So then we'd pick the fish up out of the water, and it'd be like, hey, I detected this thing. And we basically, program, if these kind of sensory inputs happen, that's a rip. So then we take it to the next beach, Chanafara Beach, throw it in, it swims, hits the rip, the sensors give it the same pattern, and then the fish robot knows, this is the rip, and it can react accordingly. It can swim up the rip, swim down the rip, behave in certain ways around it.
Cool. Yeah.
We're not at the fish stage yet.
It's exciting, though, isn't it?
Yeah, we're getting there.
You gotta know why you do it, right? So like we're building the basis to build on top of it. It's always step by step. You want to build the fish robot and throw it in the ocean, but you first got to do a nice foundation, a nice solid foundation on which.
So Arnie isn't expecting our oceans to be overflowing with fish robots anytime soon.
Realistically, this is fundamental research. Like, we might see it on an experimental craft in the next 3 to 5 years. Deployment in like large scale, commercially available things, maybe 10. Cheap, maybe 15 to 20. So I'm being very pessimistic.
When, not if, this smart sensing robot fish is produced, it could be used in many different ways.
Yeah, there's multiple applications. I mean, it ranges from like kind of what you think of like the marine biology thing. Where you want to survey reefs with coral bleaching and like biodiversity loss. It's a big thing. Then you have the, let's say, more financial aspect or the infrastructure aspect where you have a lot of infrastructure underwater. You have oil rigs, you have pipelines, you have optic cables bringing the internet from the US to here, these kind of things, and you need to monitor them. So you need things that can swim up and down, basically. Long distances needs to be very energy efficient. Currently not possible with the drones. And then comes the security aspect. So like, basically you want to make sure that nothing happens underwater that threatens the security of your ships, your harbors, those kind of things. And having silent observers, basically, that can alert you to potentially threatening situations would be quite helpful.
And since we're dreaming big right now, Arnie can also imagine incorporating Derek and Cheng Huan's work on underwater communication tools into a fish robot.
Let's say your fish robot, you put it on a reef, it swims around for a couple of hours, and the weather conditions change, you need to go home. You send a signal through this acoustic modem down to the fish robot, or generally into the reef. You don't know where your fish is, but you send it down, say, come back here, and then the fish robot will take the appropriate steps to try to come back to your boat, maybe swim to the surface and then send out a GPS signal. It tells me, like, hey, I'm 50 kilometers away from you, you got to come out here now and pick me up. Like a teenager, basically.
Yeah. With Arnie's sensors, Robert Millward Cooney's artificial muscles, and Derek and Cheng Huan's communication tools, the ability to better monitor our oceans is closer than ever. And as Ian says, it can't come quickly enough.
We got to get there one day and explore our planet. We need to be able to know what the status of our reefs are. We're getting invasive species coming in. We don't know they're here until it's too late. We just don't have a good hand on the pulse of what's happening in our own aquatic environment.
Thanks to Liz Garton for producing this episode of Our Changing World, and to Professor Ian Anderson and his team at the Auckland Bioengineering Institute for showing Liz around the biomimetics lab. Production help was by Ellen Rikers and sound engineering was by Hamish Weber. Pictures and other info related to the story can be found on our webpage, rnz.co.nz/ourchangingworld, and you can also sign up to our monthly newsletter there. If you want to chat, you can email us at ourchangingworld@rnz.co.nz, and you can also follow us on Facebook, where we are at RNZ Science. Now, RNZ is releasing new podcasts all the time. I recommend you check out Sci-Fi Sci-Fact. It's a podcast that looks at the intersection between fact and fiction, and a bunch of new episodes are up now. Te nā koe I whakarongo mai. Thanks so much for listening. Ko Clark and Canon aho. Have a great week. Kia pai, te wiki.